Hello everyone. So today, as promised, I'm going to go over a more practical example in C. So today is basically just going to be focusing on graphs. We already did graphs in the first phase of the semester, but I just wanted to take this opportunity, since you now learned the C programming language, to actually go over a more involved practical example in actually coding, a graph. And hopefully later on in the lecture, we can also look at a few applications of graphs to conclude, graphs. Okay, so we're going to do this in C. And whenever you start, a relatively big problem like making a graph, it's always best to actually draw a picture so that you really know what you're doing. So in the previous phase, in phase 1, we implemented a graph using an adjacency matrix. So, just to explore different options, we're just going to go for an adjacency list instead. If you remember, an adjacency list it can potentially be more space efficient than an adjacency matrix, because each node that's in your linked list is only going to correspond to whatever is actually connected to a given vertex. So instead of having an adjacency matrix where you might store a bunch of zeros that corresponds to no connection, an adjacency list will literally only have the nodes that correspond to the neighbors of each vertex. So let's try to draw that out in terms of actual C code. So let's first define a few different structures. Just like how in a linked list, we made a structure that would correspond to a node. Now we're going to have, a structure that corresponds to a vertex. So let's define something called vertex, okay? And let's say that it looks something like this. We're going to give it an int ID. So this is going to represent, whether we're at node 0, node 1, node 2. And, for convenience, I'm just going to leave it in terms of a typical int. We can have a weight. So we're just going to go for a weighted graph. And this weight is going to correspond to what is the weight going from some other vertex to this vertex. You're going to see what I mean in a second. So there's weight. And since we're trying to implement a linked list or an adjacency list version of this, we're also going to have a next. A struct. Let's call it a struct node. And then you'll have a pointer to next. So this type is going to be the same as this type here. So in C, I'm going to type def. I'm going to call it vertex. But what it actually is, it's just going to be of type struct node. OK? So this is a struct node, but another name for that is going to be vertex, as we're going to code later on. OK, so this is a vertex. Now, there are, this is great for implementing just a graph by itself. But later on, we're actually going to go into a few other algorithms in graphs, which will require a little bit more information for this. So I'm just going to draw this now, and it's going to make a lot more sense later on in the video. So I'm going to make something called vertex info. And I'm just going to, and that's again going to be a type def that corresponds to a struct node info. And this structure going to hold some other information that I'd like to keep track of with this vertex. So specifically, this is going to have to do with depth-first search that we'll do in a little bit. So vertex info, for each vertex, I'd like to keep track of a color. Okay. If you remember from the depth-first search lecture, you'll remember that as we traversed each of the nodes, you'll remember that we colored a node green, and then that was to specify that we had discovered the node, and then we colored it something else when we were done with that node, and we started, going back from, the furthest depth that we went in depth-first search. So I'm just going to keep track of all the different colors of each node. So there's color. We can also keep track of a parent. So struct node info, and then we have a pointer. So this is going to be the same type as this whole thing. Okay, so struct node info. Basically, whenever we're traversing the graph, sometimes it's nice to keep track of, what is, the previous node that I traversed from. So that's going to be this parent member here. Now there are a couple different things that are going to be specific to depth-first search, and we didn't go over it in the previous depth-first search lecture, but typically in depth-first search, we like to keep track of when did we discover a node, and when, so basically that's when we first saw the node, and then when are we done with that node. So in the previous lecture, whenever we colored a node green, that will correspond to when we discovered the node. And whenever we, colored it gray, so specifying that, we're done with that node and we don't want to ever traverse from that node again, that would be a finishing time. So we're going to define an int discovery time, and then also an int finishing time. Okay? So these two things, so this is going to correspond to all those nodes in your linked list. We're going to have a bunch of, adjacency lists, right? And this is going to be like our node. And it has a next, so it's very equipped to have, be a linked list. And this is just going to hold all of the other information that we want to keep track of during our, let's say our depth-first search algorithm. Okay? So let's keep that in mind. And now let's try to draw how is this actually going to look? How is this all going to interact with each other? So let's start off with making an actual graph. Let's say that that's also a structure. We can define a graph, which is going to make use of all of this. Okay? So we're going to have a graph. And what do we want to hold? Well, we want to hold basically that and that, right? And, regarding that, with the linked list node, we want to make sure that we can have a bunch of linked lists, right? Because each linked list is going to correspond to one of the vertices. And then the linked list, the nodes in the linked list will actually hold the neighbors of that vertex. Okay, so we're going to want, that vertex type. So we're going to want one of the members to be a vertex. Okay. Now, since one of those, since we have maybe one linked list for a vertex and another linked list for, vertex 1, another linked list for vertex 2, and so on, we're going to need to have a pointer, right? Because that's how we, implement linked lists typically. But since we have multiple linked lists, that means we're going to kind of have, an array of those linked lists, right? So what better way to implement that? Well, we can just use a double pointer. So, we can add a star, star, oops, kind of ran out of space. So we can call this adjacency underscore lists. And so this is going to correspond to a bunch of different linked lists, heads. Okay? Another thing we can have is that guy over there, vertex info. Vertex info. And we're going to have multiple vertices. I'm not really sure how many vertices we'll have because the way we're going to code it is that we can have any number because we'll be using dynamic memory. And so the way that we can do this is just make a pointer. So we're not going to make strictly an array of vertices. We're going to make a pointer to vertex info so that we can call malloc with this, set it equal to malloc of something, and then maybe if we want to add another one, we can do a realloc. Okay? So that's that. And for convenience, we can also keep track of how many vertices are actually in this graph. So let's just call that int num vertices. Okay? And these are really the three things that we really need for our graph. So adjacency lists, let's say that adjacency lists is this variable over here, and that's a pointer to vertex. So what does it look like? Well, we can draw it out. So imagine this is in memory, and this is just going to point to another place in memory, right? Because that's what pointers are. Doesn't matter if it's a pointer to pointer or a pointer to pointer to pointer to pointer to pointer. Really, it's just an address of whatever it's pointing to. So this is going to point to, let's say, another pointer, right? And that is going to be of type, well, vertex star, right? Pointer to pointer was going to point to just a single pointer to vertex. All right? Points to that. And, it'll point to one of these vertex stars. There could be multiple of them. There could be another vertex star here. Another vertex star down there. And, all of these are just going to be of type vertex star. And what does vertex star point to? Well, when we start actually populating our graph, this is just going to be the head of one of the linked lists, right? So this is going to be a pointer to actual vertex structures. So of type vertex only. Okay? So this vertex is going to hold an ID, it's going to hold a weight, and it's also going to hold a next, so a pointer to another vertex. So I'm going to draw it like this. So this might point to another vertex, and this might point to another one. And eventually, as you know with linked lists, the terminating node is just going to have a next value of null. You know what? From now on, null, I'm just going to specify that as an x, okay? Just for easier viewing. So all of these are of type vertex. And I might have another one. Maybe this one is just, it only has one neighbor. And maybe this guy, or who knows, maybe this guy doesn't even have a neighbor. So maybe this guy is just a null as well. Okay, so this, and how I'm going to do it is that in the order of which I have these vertices, that's going to correspond to a unique vertex. So let's say that this has an ID of 0. This has an ID of 1. And this would correspond to an ID of, let's say, 3. Yeah, it's kind of hard to, yeah, so technically this is a pointer to whatever would be connected to it. But by the position of this, this corresponds to which vertex is going to be the one connected to all of the neighbors here. So you know what, actually, to be more precise, this doesn't actually have ID equals 1, ID equals 2. Let's just label the indices of where these guys are. So this is the 0th one, this is the first one, and let's say that this is the second one. Okay? So what will this look like? Well, let's say that this has an ID of 1. This has an ID, so an ID of 1. This has an ID of, let's say, 2. This has an ID of also 0. Let's say this guy has an ID of 2 over there. Okay, so what would this actually look like as a graph? Well, we would just read it off. So we have the graph at ID 0. So this is 0 node. It has 1, 2, 3 neighbors. And a neighbor, so we're going to use directed graphs, right? 0 goes to an ID of 1. It also goes to an ID of 2. So that corresponds to this guy here. And then it also goes to an ID of 0. So it has a self loop like that. Now we go to 1. So the next guy has an ID of 2 as a neighbor. So that means 1 goes to 2, and that's it. And then 2, well, that doesn't point to anything. So that means 2, we don't do anything else. 2 has no neighbors. It has no outward going arrows. So we can just, leave that initialized as null, for example. Okay, so that's kind of like a visual representation. This corresponds to what we're actually going to code up. And this is just an example that is shown by that. Okay? All right. So now that we've went over that, let's move on to actually trying to program, a graph. Okay? So how we're going to do it, we're going to just divide it up just like how we did in the demo last time. So we're going to have, a file that has the main, that's going to call our graph functions. We're going to have a file that calls, a file that actually has the functions. And then another file that, for a header that declares all the functions that we need. So let's try to program it up. And, we can start off with actually implementing what we drew on the board. So a few functions. So, the first step includes standard I/O. Since we're going to be using dynamic memory, we'll use the standard lib. And, let's maybe, no, you know what? I'll go for the other defines later on when we actually need them. Okay, so let's start off with our vertex that, you guys all know and you saw on the board just now. So we're going to do a type def, as I was saying before. And we're going to make a struct node. And that struct node is just going to have a few different members. So one is going to be an ID. One is going to be a weight, because we're going to just allow a weighted graph. And then we're also going to have a next member. struct node star next. And we're going to call all this a vertex. Don't forget that semicolon. Okay, so that was for the struct node. Now let's also make, as I said before, a struct node info. Struct node info, we're going to have a color. We're going to have a parent member, our discovery time, and a finishing time. Let's just call that vertex info. And now we're ready to make our actual graph. So type def, let's call it just a struct. I don't need to use a structure tag like I did in the previous two structures, since one of the members is not going to be of the same type. Oops. And so what do we have? Well, we had a vertex. And we're going to call that all of our adjacency lists. We will have a vertex info, which is, we can just call it all our vertices. And then if we want to keep track of how many vertices we have, just call it int num_vertices. All right. And we're going to call that a graph. Okay? Okay, cool. So now let's try to come up with a few different functions that we're going to need. So we're definitely going to want to actually be able to create the graph. So let's make a function that actually returns, let's say a pointer to a graph. And, what are we going to need to create a graph? Well, typically, we're going to want to know how many vertices there are. So let's just pass in an int. That's just going to correspond to the number of vertices. Another thing we might want to do is know how to actually create a node. Okay. We want to know how to create a node. And, to create a node, we might want to know the identity. You know what? Let me just actually put in what I mean here. Because, you don't actually have to put in the name of the variable when you're declaring functions. So when we create the node, we can give it an identity. So that's going to be like 0, 1, or 2, and so on. And when we create the node, we also want to know what is, what is its weight going to be. So that's creating a node. Another function that we can do is to actually add a node to a certain graph. Okay, so this is going to correspond to, if we have five vertices and we want to add a sixth vertex. We're going to need some sort of function that actually dynamically allocates the memory for that node, and also reallocates how much memory is pointed to by the adjacency lists member and the vertices member as well. So there's adding the node, and then we might want to also be able to add an edge. So that's going to add an edge to a certain graph. We're going to want to know what is the source ID. So what is an edge connects the source ID to the destination ID. So we're going to want to know what are those two IDs. So there's a source ID, there's a destination ID, and we will also want to know what is going to be the weight in that. So, okay, hopefully you guys can still see that. Okay, getting a nod. Great. So adding the edge. If we add an edge, we should, logically know how to delete an edge. So that would correspond to going through the linked list and, actually taking away that node as a neighbor of the vertex. So we're going to pass in a graph. We'll have a source ID. and a destination ID, okay, because we want to know what edge are actually deleting. And then, after we're done using our graph, we're going to want to know how to delete the graph. So to do that, we would just pass in, well, the graph. So we're going to add a bunch of frees in this function here. So that's deleting the graph. And for visualization purposes, it might be also nice to know how to print stuff that's in our graph. So what does a graph have? Well, it has linked lists. So one function that we might want to do is to actually make a print list function. So we can pass in, the head of the linked list, which I can call, top list like this. And then another function that actually makes use of the print list function. So let's just call that print graph. And that's going to take in, a pointer to a graph, and so on. Okay, so let's see, just real quick, if there are any glaring mistakes. So hopefully there aren't any mistakes so far. So these are all the functions that we're gonna try to implement. Let's say right now. Graph funcs. Okay. So our first function that we wanted to do was actually create the graph, right? So that's going to take in a number of vertices. So let's try that out. Just going to have basically the exact same name over here, and we're just going to define it. Oh, and oh yeah, don't forget that the first thing we want to do is actually include what we just made. So we're going to call that graph underscore funcs.h. Okay, so now you can see that my editor is recognizing this graph over here. And to implement it, we're going to need to actually write the definition here. So the first thing, when we create the graph, if you look at your notes again at the box that we made for the graph, we're going to need to allocate some memory for the actual graph object. So we're going to just create a graph, create a star graph, and let's set that equal to malloc. And how big is it? Well, I don't know off the top of my head, but I know a size of function that will know for me. So I can use size of a graph. It's creating the graph. And let's try to initialize some attributes in the graph. Easiest one will be num vertices. We can just set that equal to what we just passed into the function. Okay. So we passed in num vertices. We're going to set that equal to num vertices like that. And yeah, okay. Next we have our adjacency lists. Adjacency lists. Oops. Yeah, it's not an underscore. It's a right member. Equals, we're going to just malloc that too. You'll set that equal to, well, how many vertices do we have? We have num vertices times and the size of a vertex star. Okay. So remember, adjacency lists, that's just a pointer to a pointer, right? So that means that whatever it's pointing to, it's going to point to a bunch of vertex pointers. So that means we need to, we're going to allocate num vertices. So that's how many linked lists there are, times how much space do those pointers actually take. Not the actual vertices, not the actual vertex structs, but the pointers to the vertex. Okay. Oops, so that was that. Next, we're going to set the vertices thing. So the vertices member to malloc. We're going to allocate memory for this too. And it's going to be exactly what you expect. So num underscore vertices times the size of, well, that's going to be a vertex info. And there we have it. And now to initialize, each of those pointers, the vertex stars, to initialize them, we can just set them all equal to null. Int I equals 0, I less than num vertices, and then we can go I plus plus. And we can just set the graph adjacency lists. Remember, that's just a pointer, so we're going to dereference that and get the ith vertex star. We're going to set that equal to null. Okay? Then after we're done, we can just return the graph. Okay? Great. So the next function that we made was this create node function. So we made create node. Let's try to implement that here. So when we're creating a node, what we really want to do is, we're actually going to start off just like in the last function, is actually make, our vertex star. So let's call that new node. Set that equal to malloc, of the size of a vertex. Okay. Now that node, it has, 3 of those members. So the new node, it has an ID. We want to initialize it with a certain identity. It'll also initialize with a certain weight. And since we're only creating a node and we're not setting its neighbors to anything yet, let's just set the node's next attribute or member equal to null. Okay? That wasn't too bad, and there's a little mistake. Sorry. So that's creating the node. Now the next function is to actually add the node to the graph. Okay, so let's take that function. So we're going to add a node to the graph. So it's going to take in a graph star. The first thing we're going to do, so remember this add node function, let's suppose we're already given a graph that has like 5 nodes, and we want to add a 6th node to it. This is what the function is going to do. So when we add the node, the first thing we're going to do is, well, increment the number of vertices, right? Because, it used to be 5. We want to be up to date. So now it's going to go up to like 6 or something. Next step, well, the adjacency lists. Remember the adjacency list, that was a pointer to, let's say, 5 vertex stars. So now we're going to have to reallocate memory so that it can actually, have a 6th element, a 6th pointer. So we're going to call realloc. And, the first argument is going to be the pointer that we want to reallocate. And then, the next one is going to be the new size. So that's going to be just graph number of vertices times the size of, oops. Oh, it's just hard to see. So number of vertices times the size of, oh man, sorry you can't see that, of a vertex star. Okay. And that's good because, the graph num vertices has already been incremented in the previous line over here. Let's just check that all the parentheses are okay. So you have realloc, graph adjacency lists, graph num vertices times the size of a vertex star. And of course, don't forget that semicolon. Okay. So that's reallocating memory for the adjacency lists. And if we want to initialize that last pointer, just like how we did above in the create graph function, we can just set graph adjacency lists at its last element, so num vertices minus 1 equal to null. And now, since we do also, remember, we have that other member called vertices, remember? So that was of type vertex info. That's also going to get an extra node. So we're going to have to realloc that, get our original vertices, and what's the new size? Well, that's going to be num vertices times the size of a vertex info. Okay. And that's pretty much all we have to do with add node. So now, if you were to look at your notes again, and you know how we drew 3 of those boxes, that I labeled 0, 1, and 2. Now imagine just having a third one. So, sorry, a fourth one that has, corresponds to like an idea of 3. Okay? And of course, I didn't draw the actual vertex info vertices member, but you can imagine having another node for that. Okay, so that was adding a node. The next function is to add an edge. Okay, so when we add an edge, that's going to require our graph, our source ID, our destination ID, and what is the weight of that graph, or of that edge. So when we add an edge, well, the first thing we're going to do is actually create a new node, right? Because we're basically going to be appending something to one of the linked lists. So we're going to create a new vertex, and luckily we already made this function up here to create a node for us. So let's just call that function create node. And what are its arguments? Well, we're going to want to know the identity. So that's going to have an identity of our destination ID. And the next argument that we will pass will be the weight. Okay, so that's all we want to know. It's the destination ID because that's going to be the node that is being pointed to by one of the vertex stars in the diagram. Okay, so we create our new node, and we're going to set a few things. So, oops, our new node next, this is going to be our new head, basically, right? So we're going to set its next to the current head that we have. And what's the current head? Well, that's just going to be graph adjacency lists at the source ID. Okay? So we're adding that. And next, we're going to set the new head. So graph adjacency lists source ID is going to be equal to our new node. So this is where we're actually setting our new head. Okay? All right. So that's adding an edge. And that's pretty much all we have to do for our graph here. Next function, delete an edge. Oh boy. Oh, hold on. Forgot I have a mouse. So let's create delete edge that will basically, delete, kind of similar to what we did in add edge. It's going to delete a node in one of our linked lists. Okay, so delete edge Well, to do this, we're going to keep track of a few temporary variables. So let's create 2 pointers. Okay. And we're going to initialize, initialize the prev node variable to null. And we're just going to create this cur node variable to iterate through our one of our linked lists. And which linked list are we going to go through? Well, we know the source ID, so we're going to use that information to know which of our, num vertices linked lists we're going to go through. So we're going to do for cur node equals, we're going to initialize it to adjacency lists at the source ID. Okay. Then, that's what we initialize it at. We can then, our condition for our loop will be that the cur node is not equal to null, so that, we stop when we reach the end of the linked list. And also, the cur node, its ID, does not equal the destination ID. Okay? And then what are we going to do after each iteration of the for loop? Well, we're going to keep track of our previous node, and that's going to come in handy if we were to delete one of the nodes. We want to keep track of what is the previous one so that we can actually link the two of the nodes together. We're going to just set prev node equal to the cur node. Okay, so update the previous node. And the next thing we can do is set the cur node equal to, well, its next. To its next member. Okay. And that's basically all I need to do in my, my for statement here. So this is kind of an unconventional way of writing a for statement. Usually you'll see a for, and then you'll have like a compound statement, and then you would have something in the loop. But really all I need to do in this for loop is just keep iterating through my list until I reach my condition that I either reach the destination ID or I reach the end of the list. So really this is actually all I need to do in my for statement, and by the time I'm done this for loop, I'll know that one of the terminating conditions is met. Okay? So that is, getting through our linked list. Now we can check a few things. So if we indeed reached, the end of the linked list, so basically if cur node equals null, another way to write it is to write if just not cur node. Well, that means that we couldn't do anything, right? Because we tried to delete an edge from a source ID to, a destination ID that didn't even exist. It's like we tried to delete from node 2 to node 3, but, well, 2 to 3, that edge doesn't even exist. So 3, the destination ID, is not in the linked list of 2. So we're just going to return out and not do anything. So the destination node does not exist. Okay. Well, if that doesn't happen, and instead, let's suppose our previous node is equal to null. So if our previous node is equal to null, that basically means that where the destination ID is actually the head of the linked list, because basically we tried to go through the loop, but we already reached our condition that the current node, its destination ID, or its ID is equal to the destination ID at the first iteration of the loop. So that means that the previous node is still equal to null. So that's the case, which is a bit different from if what we tried to find was within the linked list. It's a bit different if it's actually the head, because now we need to change what is the head going to be. So if not prev node, and this corresponds to destination node is the head of the linked list, then what we got to do is, set the graph adjacency lists at source ID. So this is the head of the linked list. Oops. Equal to graph adjacency lists at source ID and set it to its next over there. Okay, so we're basically setting the head equal to its next. Now else, this is like the most typical case. So this means that the destination node is somewhere else in the linked list. So it could be the second, it could be the last element in the linked list. This case should take care of it. Now this is why we really wanted to keep track of a previous node, because the previous node is just going to be the node before the node we want to delete. So we can set the prev nodes next equal to the cur node, to the cur node's next. Okay? Now in both of these cases, in the if and else, the current node is still pointing to the node that we want to delete. So as you remember, since we did dynamically allocate that in our create node function at some point with malloc, we're going to also need to free it as well. So after this, we will have to free the current node. Okay? So notice how in the first if statement here, if the current node ended up being null and wasn't there, I just return out. And that's okay because, I don't actually want to free anything in this because it doesn't exist. So that's why I return early and I never reach this free over here. Instead, if it does exist somewhere, either at the head or somewhere else in the linked list, then I'm going to free my current node. Okay? So that is how to delete a single edge in a graph. Okay? Now the next guy, well, what if we actually want to delete the entire graph? So we're like, you know what? We're done our algorithm and we want to run Valgrind clean. Let's delete a graph properly so that we can actually get out of the program in a sane manner. So to make the delete graph function, well, we can do vertex star temp head. Okay, vertex star. You can create a temporary head variable, and basically we're just going to keep on deleting each of the nodes in our list. So we can do something like you can iterate through int I equals 0, I less than how many vertices there are, I plus plus. Now this this loop that I'm going to do here. So remember this is So remember this for loop. Iterate through each vertex basically. Now for each vertex's neighbors, I'm going to just free it. So I can do something like while graph adjacency lists at I. Okay, so basically when it's not no longer null. Let me set some sort of temp head equal to graph adjacency lists at I. Graph adjacency lists. If I am going to set that equal to whatever is the next. Okay, so remember temp head is holding now the node, or is pointing to the node that I actually want to delete now, which is the temporary head. So of course, after I'm just going to free my temp head. Okay. Now as I go through this whole for statement, this basically deletes all of those vertex stars that you saw in the diagram. So each of those 3 vertex stars, for example, if you had only 3 vertices. Next, what I'm going to do is actually free whatever is actually still holding memory in the graph itself. So remember, the graph had adjacency lists as a double pointer. It had vertices as another pointer, and of course, well, we had memory for, well, the graph itself. So we're going to do 3 frees. We're going to free, well, our adjacency lists, right? Because that was just another pointer that we had allocated up here when we created our graph. So remember, this was a malloc. What we have to do, since we malloc this, we're going to need to free it. And since we also mallocked for our vertices member here, we're going to need to free that too. So free, graph vertices. And then, well, remember when we created our graph, we started off by setting graph equal to malloc of a size of a graph. So we're going to need to free that as well. Okay? And now this should be all we need to actually delete our graph. Okay? All right. So now a few auxiliary things that we might want to do is to print a list and also print the graph. Just so that we can really see what we're doing here. So to print a list, and I'm sure a lot of you guys have already implemented this when you're implementing either lab 3 or lab 4. So to print a list, we can set a temp node equal to the head of the list. So I'm going to call that top list. And then I'm just going to, while the temp node is not equal to null, so I can just say something like while temp node. Let's just print, we might as well print the ID. Okay. So the ID and, whatever it's, pointing to. So we're going to print that. And then we can, to format that, you would have the temp node, its ID. Okay. And then I'm going to set the temp node equal to temp node next. Okay, so that's how we print a specific list. And then after that, if we want to be really complete, we can also print, let's say null and a \n. Okay, so basically you can expect if we have if the neighbors of vertex 0 are 1, 2, and 3, you should expect a 1, arrow 2, arrow 3, and then a null, or an arrow to null. So that's printing the list. Next, we can print the graph itself. So to print the graph, we can start off with a little label and say that, oh, this is going to be a bunch of adjacency lists. Let's say that, oh, nope, let's not print anything else. I think that should be enough. Oh yeah, don't forget, let's put a \n so that it looks not too messy. And then the next thing that we're going to do is to iterate through each of our different IDs. So remember, the number of IDs is just going to be graph num vertices. Okay. And then let's just print, first of all, what vertex are we on? So in that in the list of vertex stars that we had in the diagram, we're going to have vertex, let's say mod D, and I'm just going to give it ID. now that we're at, our certain vertex, we can call our print list function that we did. So we're going to pass in graph. And what did it want? It wanted a vertex star, so we wanted to give it a head of our list. We'll pass in graph arrow adjacency lists, and which one? Well, given by our ID over here. Okay. So that's great. And after that, if you want to, again, make it look nice, you can add in a \n as well. Okay, so this is all we need to actually code, a graph in C. We haven't done the algorithms yet, but we'll get to that soon enough. But yeah, so this is what we need to make. And the next thing that you'd want to do is actually, call the functions that, we made. So to do that, we can, go to graph main lec. We're going to, of course, include our graph underscore funcs dot h. We're going to have our int main void. We can return 0, if we want. And what are we actually going to do in this? Well, let's start off by actually making a graph. So we're going to do graph star graph equals create graph. And, how many vertices do we want to do? Well, let's try to follow some proper practice here and actually define maybe some macros, in our header file that we had. So in graph funcs.h, let's say that we want to define num vertices, and let's say that we want to do it as 9, for example. Okay, so that's not too bad. We can set that equal to num vertices. Now remember, this isn't constraining how many vertices we can actually have in the graph. This is just initializing how many vertices are going to be in the graph, because the way we coded it, we made an add node function that actually allows us to reallocate memory. Okay, so don't think that we made a graph that's constrained for like 9 vertices. I'm kind of just taking this as an opportunity to show you, where we might want to add like a define macro. Okay, so that's creating the graph. And then the next thing that we might want to do is actually add some stuff to the graph. Oops. Okay, so we might want to, let's say, add an edge to our graph. And let's suppose, our source ID would be, let's say, 0. Our destination ID might be 2. And maybe the weight would be 5. As you can see, it's kind of useful. Visual Studio's nicely reminding me of what these arguments are. And just since for testing purposes, let's not do too much. Let's print the graph like this, because we made a print graph function. And next, something else we can do is also, well, delete the graph. Or maybe we can delete the edge between the graph, between, also 2 and 5. That could be another thing that we do. And then if we want to add more edges, we could have also done a few other add edges as well. So maybe you want to add like 1, 4, 2. You can add to vertex 1 destination of also 0 and 5, so a weight of 5, and so on. We can just keep on adding edges to our heart's content. We can also, if we want, we can also add a node to the graph. And then, so you can add the node if you want. And you know, the end of the day, at the very end, we're going to have to delete the graph if we want to run Valgrind clean. Okay, so this is just an example of how we can actually use, you know, the functions that we just made. Okay. So that was actually creating the graph for you guys. So since hopefully you guys followed along, I'm going to just let you actually try to test this out. I haven't tested this out, obviously, because I just coded this in front of you guys, but try to test it out, see if that works. If there's any errors, I'll just show you guys. I'll just quickly update that for you guys later on. But you know, since we don't want to take too long, I do want to move on to something else, which is actually getting into depth-first search in a little bit more detail. Okay. All right, so graph applications. Okay. Slideshow from beginning. Okay, so graph applications. So we're going to first, you know, kind of explore. Sorry, let me just set up real quick. Okay. Oops. Oh, perfect. Okay. So graph applications. Now we're going to just revisit depth-first search over here. So now the algorithm with depth-first search, as you saw, basically intuitively, we're trying to just, you know, we start at a certain node, and then, you know, at that node, we're going to just, you know, keep on going, you know, as far as we can until we can't. And then we'll start backtracking, and then, you know, we'll eventually be done our whole traversal of every single vertex in the graph. So in pseudocode, now I'm going to show you a little bit of a different implementation. Before you saw it implemented with a stack, but if you remember, you know, stacks, you know, is just a way of implementing recursion. So this code, the pseudocode that you see here, is a way to make it, you know, a little bit more concise, because I'm making use of recursion, and I'm making use of the function call stack implicitly. Okay, so depth-first search, if you remember, you start off at a certain node, and we're going to follow a convention where we're going to actually color these nodes, and they're going to have a significance. So if it's white, that's going to denote a vertex we never visited before. If it's green, as we kind of followed in, you know, in a previous depth-first search lecture, green will denote that we actually visited the vertex at some point. And black will denote, and I think in the previous slides it was actually colored as gray, but here we're going to show it as black so that you can, I think, see it more easily. Black will denote that we actually finished at that vertex. So let's start. And oh yeah, another thing we're going to do, we're going to add in a discovery time and a finishing time. Okay, so that's useful if we want to keep track of, you know, when did we actually reach a certain node. Okay, so discovery time, whenever we color a node green, we're just going to set that equal to the current time. Whenever we color it black, we'll set the finish equal to whatever time we have. And the time variable that I'm referencing to, that's just going to be a global variable that is going to keep on incrementing as we explore one vertex at a time. Okay? So the first step, you know, we start at 0.
Next, after we color it green, well, we're going to look at all the neighbors of, this 0 guy here. And basically, if it's white, so like 2, for example, then we're just going to call depth first search, or this explore function that I called it, on that node itself. So we reach 2, we color it green, and then we're going to look at its neighbors. So we're going to look at 3 and 5. So let's say that we look at 3 first. Well, we're just going to do it again. We're going to call depth first search on 3. Let's say we look at 8 before we look at 1, so we look at the 8 neighbor first. And then we call explore on 8. And notice how I'm keeping track of these discovery variables so that we can keep track of which one did we go to first. We then explore the neighbor of 8, which is 7. Explore the only neighbor of 7, which is 9. And now, in this loop over here, after we reached the 9, we colored it green. We're going to look at all the neighbors of 9, but if you look, there are no neighbors in there. There are no neighbors in 9 at all, so we are done this for loop here. So we reach this part of the code where we actually color it black. So now it's colored black, and we set its finishing time to 7. Okay? So we finish that, and now we go next. Since we went through all the neighbors of 8, we exhausted it, we finished 7. Now we color 7 black. And afterwards, how do we get to 8? Well, we reached that before with the 3. So we color 8 black. The next step will be to color the neighbor of 3, so this 1 green. Okay, so we color it green because we didn't discover it yet. And then we call depth first on the 1. So on its neighbors, that's 4, hasn't been discovered yet, so we color it green, and so on. Now we're done for. None of the neighbors of 4 are legitimate because, it's black, it's not white. So we are done with this guy, and we color it 4, or we color it black. Sorry. Similarly, we're done with the 1, and we color it black. Afterwards, how do we get to 1? Well, we got to it from 3. So we're going to color 3 black because it has no more neighbors it can really explore. And next, how do we get to 3? Well, we reached it by 2. But remember, 2 is not done yet because after we're done with 3, then we go to the 5 here because that had another neighbor that we haven't explored yet. So we go to 5, color it green. Now we're at green. We're at 5. Now we look at the neighbors of 5. Well, there is a white neighbor. There's 6. So we color that green. Look at the neighbors of 6. We see a 3 and a 7. None of them are white, so we're not going to explore anymore. We're done. And we color 6 black. Now we're back at 5. We look, and we see that the 6, is not white. It's now black. And we color 5 black. Similarly, 2 will be colored black, and 0 will be colored black as well. Okay? Now, what do we do here? What we did is, after depth first search was done, we did that in 20 iterations, and try to think about what will be the complexity of depth first search in terms of the number of vertices and the number of edges. If you think about it, you'll notice that we went through each of the different vertices in the graph. So that's going to have V, let's say. But we also went through every single edge and we processed it at least once here. So therefore, we'll have a complexity of O of V plus E. So number of vertices plus the number of edges. So another thing with depth first search is that we can classify different edge types. So a tree edge, for example, is just going to be each of these green arrows that we just made. Whenever we explored from a node to a white node, we call that a tree edge, right? Because we're kind of creating a tree that corresponds to how is depth first search actually traversing, in the forward manner. We can define a back edge as whenever we explore from a green node and we look at all the neighbors, and if we notice that there's actually a green node instead of a white node. So we can call that a back edge. And if you look at slide 12, if you go back to that, you'll see that that is where we can notice that we made a back edge. Okay? So that's the back edge. And then there are a couple other edges that correspond to other types. So there's no forward edge in this graph. This corresponds to if we have a non-tree edge such that the next, this guy, like if we have an edge AB, B is a descendant of A, and by descendant I just mean that, for example here, 1 is a descendant of 0, okay? So if there happened to be an edge from 0 to 1, so if you flip this red arrow here from 1, 0 to 0, 1, this would actually correspond to a forward edge. There's also a cross edge, which basically corresponds to every other type of edge that isn't a forward, back, or a tree edge. Okay? Now, why do we care about these different edge types? Well, the most important edge type, really, is the back edge here. So in a graph, one application of a graph is to actually know whether there is a cycle that's somewhere in the graph. Now, we're not going to prove it, but you can show that if you have a single back edge in a graph, then that warrants that there is a cycle in the graph. Because the back edge will always, complete part of the cycle. You can kind of intuitively see why that is. You can see here that, we make a bunch of tree edges like this, we explore, and then this back edge corresponds to an edge pointing from here to one of its ancestors. And the ancestors are shown only by the tree edges here. So that's where our cycle is. Okay? Whoa. Okay. So that's really useful in cycle detection. And applications of cycle detection might be, let's suppose your graph wanted to represent, a certain schedule. If you're trying to schedule a bunch of different events, they could be like real-time events. They could be scheduling, for your CPU. Let's suppose we wanted to model, courses that you're taking in school. And each edge between one course node and another course node would show that if there's an edge from one to the other, like let's say ESC180 to ESC190, ESC180 node would have an edge towards the ESC190 node, because ESC180 is a prerequisite of ESC190. Now let's suppose we have a huge graph that has all of the courses, and one is a prerequisite of the other. Then the graph, if you want to really make sure that the courses that you're taking are okay, you can run a cycle detection algorithm here. So by doing cycle detection, basically if you ever have a cycle within your space of courses, then you know that you're not doing something right. You're doing something illegal. There's no way that you can take the courses that you really want to take like that. Okay? And then also deadlock in operating systems, which is a little bit more of an advanced topic that you might see in a third-year course. Now, a very, very important application that has to do with cycles is topological sort. So this is another type of sorting algorithm, not the typical one that you would see that we covered last lecture or the previous one. In a topological sort, let's suppose we go back to our courses example, and we're given a whole bunch of sets of this course is a prerequisite of this, which is a prerequisite of this, and we make a graph representation. A topological sort basically orders all the vertices such that if there's an edge that connects any two vertices, then, and let's call them A and B, then A will be before B. Okay? So if we wanted to make a plan for what courses we should take, in your space of courses, if you just run a topological sort on all the vertices, which are the courses that you might want to take, then topological sort will actually give you a valid ordering of which vertex to take, so which course to take. So this is useful also for scheduling jobs. So if you're scheduling a bunch of jobs to go, and you know that one job has to go, job 1 has to be before job 2, job 5 needs to be before job 8, for example, then topological sort will give you a good ordering of when to actually make the jobs happen. I suppose you're scheduling events, for some whatever reason, and you know that one has, a higher, let's say, priority than the other. One has to happen before the other event. A topological sort can tell you, a valid ordering of when to schedule them. One note is that the graph has to be acyclic, which kind of makes sense because if you had cycles in your graph, then, really there is no way to make sure that you can get a valid ordering. And the algorithm to run topological sort, well, this is going to make use of our finishing time that we used before. So basically how to do topological sort, just run the depth first search algorithm, and whenever you reach a finishing time, then you're just going to append that node, you're going to insert that node for that vertex onto a growing linked list. So the topological sort, if we go back, to this, basically as soon as we reach, our first, finishing, so basically our first black vertex, in topological sort, all we got to do is, modify, the algorithm such that we insert into the head of the linked list this 9 over here. So what would be the order? Well, we would have 9, and then we reach our next black node, and since we reach another finishing time, we would then append, or we would insert 7 onto it. So you would have 7 and 9, and just to draw it out as we're going through, we had 9 and 7. Okay, we kept going. Then we had 8. Keep going. We haven't reached a black node yet. Haven't reached a black node yet. Now we reach 4. So we would add the 4 to our list. And then there's 1. Okay. Then 3. And then 6. 5. Shoot. Okay. Let's just quickly delete edge here. This is not the same graph as this one, obviously. So 5. Okay. Then 2. And then 0. Okay? And this is our topological sorted list that we just did directly from just slightly modifying our depth first search. So you'll notice that 0 to 2, to 5 to 6 to 3 to 1 to 4 to 8, to 7, and then finally to 9. This is a valid ordering where any two vertices that we take, there might be an edge connecting from the left vertex to one of the vertices to the right. There's not going to be a single edge connecting, let's say 1 to one of these guys before it. So this gives a nice sorting representation of our graph. Okay, so let's see the time. It's doing pretty good on time. So that's topological sort. And maybe in a next lecture, I could go over actually programming it, but it shouldn't be too hard to implement. All you would need to do is just make use of, oops, sorry, going the wrong way. You would make use of the algorithm that I'm showing you here, and after you use the code that I just wrote right in front of you guys, all you need to do is create a couple of different functions, DFS, and let's say an explore function to actually implement each of these lines. So the only tricky one will probably be this 4W in neighbors of V. To do this, you would just need to make sure that you can actually iterate through the whole linked list that we have in C. Okay? And if you want to denote things as white, green, or black, all you could do for that is maybe set a macro. You can say white, define it as 0, green, define it as 1, black, define it as 2, and so on. Okay. So I want to move on to another very important algorithm with graphs, and that is called the minimum spanning tree. Okay? So the problem with a minimum spanning tree, this is going to be kind of similar to your breadth first search types of algorithms like Dijkstra's algorithm. But the point here is that let's suppose you're given a weighted, no cycle, so acyclic, undirected graph. We want to find what is the set of edges that will minimize the sum of all the weights and that actually connects every single vertex together. So applications for this, that's a little bit abstract to say this, but just think about it in terms of these applications here. So let's suppose you're given a map of different communities, together, and you need to actually create a sort of, a network, like a travel network that connects all of the different communities together. But let's suppose what is, what it was the distance that's between different communities. We can specify a weight if we were to represent that as a graph. So the higher the distance, we can say higher distance means higher weight. We might have a higher weight if there's a lot of obstruction in the way, and so on. So it might be nice to know what is the set of edges or roads that we should actually use to minimize how much obstruction and distance would be traveled if we were to traverse the entire city of communities. Another application is in printed circuit boards. So let's suppose we're trying to manufacture a printed circuit board or a PCB. That typically consists of a lot of components together, like maybe surface mount resistors, transistors, capacitors, and so on. And now the problem is, we drew a nice schematic. From ESC190, you drew those beautiful, schematics with like resistors, capacitors, and that's great. So you know the schematic, according to your calculations and stuff, your simulations, it all works. But it's a lot harder to actually, implement that in a tiny board. Okay, so one very common problem is, let's suppose you're given a bunch of pins. So those are like, the ends of the resistors, ends of the capacitors, and so on. And you know that there's a bunch of pins that need to be connected together, right? By some means. We want to find what is, how should we best do it to minimize the trace length that we do. So how much copper is going to be required to actually connect different pins together. And ideally, we should try to minimize how many traces we make. So that's another application of a minimum spanning tree. If you're to treat this as a minimum spanning tree problem, try to find all the edges to minimize that weight. Okay? So the general idea with how we're going to make this minimum spanning tree is to start off with, let's say, a subset of an MST, so the minimum spanning tree. And we're going to try to sequentially add edges such that our tree is still a minimum spanning tree. And then we're going to keep on doing that until all the vertices are covered. Okay? Now the trick is, how do we actually determine what is going to be a safe sort of edge that we will add? So there are two different algorithms, and we're only going to go over one of them. There's one is called Prim's algorithm, and that basically makes use of a priority queue, which we have gone over a few times before. Basically, what it does is that it adds a random vertex to your MST. We'll choose the minimum weight edge that's connecting a vertex in the MST to the rest of the graph that's not part of your MST. We're going to choose that minimum weight, and then we'll add that to the minimum spanning tree. Okay? We'll add the vertex from this minimum weight to the minimum spanning tree. And then we're just going to repeat steps 2 and 3 until we just completely build it. The other method is called Kruskal's algorithm. That's another type that actually makes use of something called, another abstract data type called a disjoint set. We're not going to go over that because we haven't done disjoint sets. That's a bit of a more advanced topic that has to do with actually knowing how to union different sets together in an efficient way. Okay? And also, both algorithms actually, but you can see here with Prim's algorithm, they're also called greedy algorithms, because from this step here, we're only going to choose the minimum weight, so the best possible, the best looking weighted edge possible to our minimum spanning tree. So that's called a greedy type of algorithm. So this is the pseudocode for Prim's algorithm, which you can implement yourself. So basically, you go through each vertex in your graph, and we're going to just initialize their priorities to, let's say infinity. So that's going to be, remember, a priority queue. It has a bunch of priorities that correspond to them. Just initialize them to the maximum possible value that they can have. The parent is going to hold, when we're building our tree, every node except the root is going to have a parent. So the parent is going to allow us to trace through, where is, how is my node connected in the minimum spanning tree. Okay, so the first step in Prim's algorithm is just choose a random vertex v. So I'm just going to call it v here. We're going to initialize its priority to 0 because that is going to be the root of our minimum spanning tree. We can choose any vertex to be the root because no matter what, the minimum spanning tree is going to connect every single node. So without loss of generality, we can just choose this v, any vertex to be our root. So we can initialize its priority to 0, right? Because we no longer need to explore that node or that vertex anymore. We're going to build a priority queue. Okay, that's going to contain all of the vertices in our graph. And then basically, while the queue is not empty, so the queue has all the vertices, we're going to then dequeue, the next vertex. So in this case, it'll be V, right? Because that's the only guy with the priority of 0. And and by the way, we're implementing this priority queue such that the lower priority gets precedence. Okay? It's kind of like it's going to be like a min heap. So we dequeue the first guy. We're going to go through each vertex in the neighbors of that vertex, and basically we're going to set its priorities equal to the weight between our current vertex and each of the neighbors of W. So let's go over that in more detail. This is the exact same graph that we used before, except now I just converted it such that it's an undirected graph. Sorry. Okay, so what are we looking at here? This is our graph, and I just added a bunch of random weights to it. And this chart over here is going to hold the priority queue and also the parents of each of the vertices. Okay? Okay, so calling prim, we're going to first start off by going to each and every one of these vertices and setting its priority to infinity. Each of the parents will be set to null because we haven't built our tree yet. Next step is to, choose a random node, and let's say I choose this guy here. Apologies that it's gray. Hopefully you guys can see it. So we're going to choose 2 as our root, and then we'll build our priority queue with all of these guys. So the 2 here, which corresponds to the gray node here, has a priority of 0. Its parent is set to null because this is going to be the root of our minimum spanning tree. Okay. Next step, well, we're going to dequeue this 2. So I'm just going to cross it right off. I'm going to dequeue it. And now 2 is our W here. Now I'm going to look at each of the neighbors of 2, so 3, 5, and 0. And what am I going to do? Well, first I'm going to set each of these guys' parents to 2, okay, because these are potential next nodes in our tree, so I'm just going to immediately set their parents to whatever I went from. So I'm going to set them, you can see 0 now corresponds to 2, vertex 2 has 2 as well, sorry, vertex 3 has a parent of 2, vertex 5 has a parent of 2 as well. Then I set their priorities. So the priority of each of these 3 nodes is just going to be set equal to the weight that connects 2 to each of them. So for vertex 0, it has a weight of 5 over here. So I set its priority to 5. Vertex 5 over here has a priority of 2 because its weight is 2, from 2 to 5. And similarly, node number 3 will have a priority of 8 corresponding to this over here. So now the next step, because I'm using, this is a greedy algorithm, Prim's algorithm is greedy, I am now going to next expand the next smallest priority. So this is where it's very, very similar to Dijkstra's algorithm. Just going to look at, in this priority queue, extract, I'm going to dequeue or extract min in a min heap. And what's the minimum? Well, that's 2, right? So out of 5, 8, and 2, the minimum is just going to be 2. I dequeue it, and the neighbor of that is going to be 6. So I'm going to set 6's parent to 5 over here. I'm going to set 6's priority to the weight from 5 to 6 as 1, and that's it for that. Next, I need to get the next lowest priority, so I look 5, 8, and 1. So I'm going to expand 6 next, because that has the lowest priority. I get 6, and I look at the neighbors. I look at 3, and I look at 7. Okay, so for each vertex A and neighbors, now notice this. 7, it has infinity and null, so you would expect its priority to change to just 9, right? It's this weight over here. But look at the 3 up here. The 3 already had a priority of 8. But since now I'm at 6 and I notice an even lower weight here of 1, this is the part of the code here where if I see if if my neighbor is in the queue, which it is, so 3 is indeed in the queue, and the weight from W, so 6, to A, which is 3, is smaller than the current priority, then I'm going to update its priority accordingly to the new weight. So since 1 is smaller than 8, I am going to set that equal to the new weight, which is 1. And of course, since now I traveled to 3 from 6 instead of 2, I'm also going to change its parent accordingly to 6. So previously it was 2, so this guy. Now it changes to 6 over there. Okay, so I continue, and I look at the priorities. Well, the min is now 3 here. It has the smallest priority. So I'm going to expand 3. I'm going to look at 8, and I'm going to look at 1. Nothing really changes much because I never discovered these before. So 1 is going to have a next priority of 7. A parent is going to be 3. And 8 is also going to have a priority of 3 up here. And the parent will also be 3. Okay, so that's done. Almost through it, halfway through. The next priority is, it's going to be 3 because that's the smallest. So I expand, I get 3 away. Nothing. Sorry, so vertex 8, which has the priority of 3, will get expanded. So that's why this is red now. And I look at the different neighbors of 8. So there's 4, and there's also 7, which was discovered before by the 6. But again, you'll notice that the weight from 8 to 7 is 3, which is smaller than the weight from 6 to 7, which was 9. So I'm going to need to update this 7's priority to 3, like right over here. So I update it to 3. The parent of 7 becomes 8. Okay, becomes 8 instead, and so on. So 1 still has the neighbor of 7 and a parent of 3. Next, so the next smallest one is going to be vertex 7 with a priority of 3. So I expand the 7. I find 9. I update 9's priority from infinity to 4, which is this weight over here. And then I again look for the lowest priority, which is going to be 9 now because it has the priority of 4. Cross it off. Nothing changes because the neighbors, there are no neighbors of 9 really that are no longer in the queue, that are still in the queue because 7 was already taken out of the queue. So nothing really changes here. So this does nothing. And next, the next priority after that is 5. I cross it off. I look at its neighbor 1. I have to update 1 because it has a neighbor of 3, or sorry, it has a weight of 3, which is smaller than this previously discovered weight of 7. So I update that to 3. 1's parent now becomes a 0. And next, the next guy, is 1 because I just updated to a smaller priority. I expand the 1, and again I look at 3. I don't do anything to 3 because that's already out of the queue. I look at 4, and so that changes. That's going to change from 6 to 2 because from 1 to 4 is 2. That's smaller than from 8 to 4. So I'm going to update that as well, such that I have a priority of 2 now instead. So now I'm done. So I have colored every single one of those nodes red, which basically just corresponds to getting, exhausting the entire priority queue. And now, if you look closely, you'll see the the orange edges corresponds to the edges in the tree. And how would you get that algorithmically? Well, here we set each of these attributes, parents, to something. So what you would do is you can start off at the root. So I can actually just draw this out. Okay. So what does our minimum spanning tree actually look like? Well, we have 2 at the root. Next, we have, let's say, 5, which has a parent of 2. Like that. What else do we have? We have number 0. So number 0 over there, which has a parent of 2 as well. So this has our 0. What else? There's also number 6, which has a parent of 5. Okay. So we have 6. And then 6 goes to 3. So 3 does have a parent of 6. So we might have our node 3 over there. And then what else? So we have number 8, which has a parent of 3. Okay. So yeah, sorry, it's getting a bit messy. And then our 8 leads to 7, and then 7 leads to our 9. Okay, so we're going to have 7, and 9. Okay. And then anything else? So we have our 0, which we have over there with a parent of 2. And then we have our 1, which has a parent of 0. Okay. And then what am I missing? I'm missing, oh yeah, number 4, which has a parent of 1. Like so. Okay. So not the most conventional looking tree, but it follows the definition of a tree, right? Because you have a root, and each node has some number of children. You have a 5, 0. Just so happens that the way that my graph is, I guess it's simple enough that, this just ends up being a big chain here in my minimum spanning tree. And yeah, you can also label each of the weights as shown on the graph. And yeah, this is how you would draw your minimum spanning tree, after you run the algorithm. Okay, so whatever this represents, either your printed circuit board, pin connections, or places in a graph or in a map, this would correspond to the minimum number of networks, minimum number of roads or traces that you can make with this. Okay, and that is the minimum spanning tree. Your homework for you guys will be to actually try to implement Prim's algorithm yourself. So using the graph implementation I gave you, and also lab 2, where you actually implemented, a version of a priority queue, so a heap. That's the data structure that you can actually use to implement this priority queue. try to combine, the graph implementation that we just coded up and also the heap to actually implement Prim's algorithm. It's not listed there, but I would also say try to program depth-first search as well, just to warm up, because that should be a lot simpler than coding up Prim's algorithm. So I'll save that as an exercise for you guys to do using my implementation. And after Prim's algorithm, that you do, try to also think about what would be the running time complexity of Prim's algorithm in terms of the number of vertices and also the number of edges. Okay? All right, so I think that's pretty much it for today's lecture. It was a relatively long one in concluding graphs for this semester. And hopefully, seeing me implement the graph in C with all the visualization that I did on the board will hopefully help you with Lab 4 as well. Okay, in the next lecture, we will go into a few more specialized topics, game tree search, and also dynamic programming. And as a reminder, those will not be primarily evaluated in the labs or your exam, but they may show up as a bonus for those of you who are really interested in learning those topics. Okay? All right. Thank you very much.